work out an example, the case of a ball rolling down an inclined plane. So the plane is inclined at an angle theta. I pick coordinates where x points up the inclined plane parallel to it. Y is perpendicular to the inclined plane, and again, it's the upward direction away from the plane. Let's step through some of the things that we know about this situation. Let's first talk about what forces are acting. We know that there is a normal force there, and it's a force, contact force between the inclined plane and the ball. And that's going to be as big as it needs to be to prevent the ball from falling through the inclined plane, and it can't be so big that it'll push the ball up into the air. It just prevents these two solid objects from occupying the same space at the same time. The ball has some mass, so I know there has to be a force of gravity acting on the ball, so there's the weight of the ball. And the ball is going to roll, it's not sliding. So there's a force of static friction at the point of contact between the ball and the inclined plane that is going to prevent this component of the weight, the part that's parallel to the inclined plane, from making the ball just slide down the incline. So there's a normal force, gravity, and a force of static friction. And we know, since it's rolling, that this force of static friction is less than or equal to the maximum magnitude it can take. All right, let's look at what we can learn from Newton's laws of motion. In the vertical direction, the ball is in equilibrium because it's not going to fall through the inclined plane. It's not going to spontaneously jump up in the air. So equilibrium vertically, that tells me that the normal force is going to be big enough to cancel out this component of the weight, the part of the weight that's perpendicular to the inclined plane. So the normal force is going to be that big, the weight of the ball times cosine theta. In the horizontal direction, my x coordinate, I add up all of the x components of forces, and that's going to give me Newton's second law of motion, mass of the ball times the acceleration vector at center of mass, x component. So I've got the force of static friction pointing up the incline, so that's positive. I have this component of the weight pointing the opposite direction along minus x. So I've got that part of the weight times sine of theta, and then the net force resulting out of that is going to give me the mass times the x component of the acceleration of the ball. Now, in this example that I'm working out for you, I am taking the rotation axis is going to be at the center of the ball. So there's my rotation axis. And to remind myself, a counterclockwise rotation is positive. So that's my direction for a positive rotation. Okay. As an exercise for yourself, you should try the same idea, but put the rotation axis at the point of contact between the ball and the inclined plane and see what that does, what insight that leads you to. So we have sum of forces. We also need to have the sum of the torques. So let's talk about that. The normal force, well, I look at that, its line of action passes right through my rotation axis. So there can be no torque from the normal force. There's no lever arm. weight of the ball, well, that's weight of the ball acts at the center of mass of the ball, and it's directed straight down. So for that rotation axis, the weight of the ball causes no torque. And again, because there's no lever arm going into that torque. We have one force remaining, force of static friction. And since this is going to start rolling, this torque can't be zero. So we have an insight that static friction causes the torque for rolling about the center of mass. Right, so now let's try to apply Newton's second law of rotations, in this case for the ball rolling down the inclined plane. And there's a curveball coming up, which is mostly why I wanted to go through this with you. It takes a little thought to wrap your head around it first. So Newton's second law for rotations. If I'm doing this about the center mass of the ball, I have rotational inertia about the center of mass times the angular acceleration alpha is equal to the net torque. And I only have one torque, so that's kind of easy. That is going to be plus the radius of the ball times the force of static friction, because this torque, there's my position vector, there's my force, and R cross F, right? R cross F is going to give me a torque that is coming out the plane of the page, and so that is a torque along what would be my positive rotation direction. So this comes in with a plus sign for the torque. I'm going to write this a little bit. R times the force of static friction, and now here comes the curveball. If I want to rewrite using the smooth rolling condition alpha in terms of A, I've got to do a little head scratching and think it through, because a positive angular acceleration for my choice of coordinates is causing a negative linear acceleration, because the ball rolls down the hill, down the inclined plane, and I picked up to be the positive direction. So you've got to draw out your coordinates, and you've got to stick to your coordinate choices. And for my coordinate choices, I have a positive angular acceleration resulting in a negative linear acceleration. So I need to have this minus sign here. So great big flashing letters. Caution. You've got to go back and look at your coordinates. They matter, right? The choice of coordinates is arbitrary, but once you've chosen, you need to be consistent. All right, so I'm going to rearrange this equation to get an expression for static friction and see what we can learn from that. So the force of static friction will be equal to minus the rotational inertia around the center of mass for the ball, acceleration at the center of mass, x component, over radius of the ball squared. And we also know from Newton's second law of motion that the force of static friction will equal the mass of the ball, acceleration at the center mass x component, plus this fraction of the weight, mg sine theta. So that was from Newton's second law of motion along the x direction. Move things around, get everything that has acceleration x component on one side, everything else on the other side. We have minus mg sine of theta. Inertia of the ball, acceleration, the center mass x component, plus rotational inertia about the center of mass over radius squared, and then again, acceleration of the center of mass x component. So I'm going to factor out that common term, minus mg sine theta is the acceleration, the center mass x component, and we have a term for linear motion, inertia m, and then rotational term, rotational inertia about the center mass divided by the radius squared. I'm going to rearrange that to get the acceleration of the center mass x component just by itself. We got minus mg sine of theta over m plus rotational inertia about the center of mass divided by r squared. I'm going to divide every term top and bottom by m. So this will simplify to minus g sine theta over 1 plus rotational inertia about center of mass, now divided by m r squared. All right. Now I'm going to do a little generalization that is helpful. For things that can roll, their rotational inertia about the center of mass has a form that looks like a dimensionless parameter that I'm just going to call beta times the mass of the object that can roll times its radius squared. And some particular cases that might be of interest. And a quick little table for rolling objects. Beta could be 1, and that's the case where all of the mass is at the radius furthest away from the rotation axis. I could have beta is 2/3 for a hollow spherical shell, so basically like a basketball. A solid disk will give me a beta of 1/2. Good, I spelled it the right way. Not British. And then if I have a solid sphere, beta is 2/5. And these are just some values that you can find tabulated in your book. Obviously, there are other ones, but this spans a good representative regime of space for objects that can roll. So if we think of this parameterized rotational inertia, it will have a dimensionless parameter in front, beta, and then mr squared, but the m and the r squared are canceling out with mr squared in the denominator. And so this will simplify to a nice form. Acceleration of the center of mass, x component, be minus g sine theta 1 plus beta. So the closer beta is to 1, I'm making this denominator larger, which means I'm making the linear acceleration smaller. The smaller I can make beta, I'm making this denominator overall smaller, which which will result in a larger linear acceleration of the center of mass as this object rolls down the inclined plane. And if no kinetic energy is going into kinetic energy of rotation, then this beta is 0, and we're back to our relation for an object that just slides down the inclined plane. Its acceleration is going to be minus g sine theta, where the sine theta is just telling you the fraction of gravitational acceleration that's directed parallel to the inclined plane.